The climb section of aircraft performance deals with the analysis of that stage of flight from takeoff to the en route altitude or cruising altitude. There are primarily two ways in which we can examine the performance of an aircraft in the climb. Firstly, by considering the angle or gradient at which the aircraft climbs, and secondly, by looking at the rate at which it climbs. We shall examine angle or gradient of climb first. Shown here is an aircraft in unaccelerated level flight. Notice that the forward acting force, thrust, balances the rearward acting force, drag. Therefore, the aircraft maintains a steady speed. However, when the aircraft attempts to climb, as shown here, a component of the aeroplane's weight acts backwards along the longitudinal axis in the direction of drag. This component is known as weight apparent drag. It can be calculated by multiplying the weight by the sine of the angle of the climb, gamma. You will now notice that the magnitude of the rearward acting force is now more than that of the forward acting force. If this situation were left unchecked, the aircraft would decelerate. To maintain a steady speed along the flight path, an additional amount of thrust is therefore needed to balance the magnitude of the weight apparent drag. This is known as excess thrust. You will notice now that the forward acting force in green matches the rearward acting forces in red, and therefore the aeroplane is able to maintain a steady speed along its new flight path. To maintain a steady climb with no loss of speed, thrust must balance not only the aerodynamic drag, but also the weight apparent drag. The larger the excess thrust available, the greater weight apparent drag that can be balanced. In other words, the more excess thrust available, the steeper the angle at which the aeroplane is able to climb. If the aircraft only has a small amount of excess thrust available, then notice now that there is too much weight apparent drag and that the angle will need to be reduced so that the excess thrust available balances the weight apparent drag. The excess thrust can be calculated by taking the total amount of thrust available and subtracting from it the amount that balances the aerodynamic drag. The remaining thrust is the excess thrust available. From what we have just seen then, for any given weight, the angle or gradient of climb depends on the amount of excess thrust available. We show here the formula to calculate the gradient of climb. Remember that total thrust available minus total aerodynamic drag gave us excess thrust available. For any given weight of aeroplane, the greater the excess thrust available, the steeper the climb angle. The smaller the excess thrust available, the more shallow the climb angle. In order to maximize the aeroplane's climb angle, then, we need to maximize the excess thrust available. In order to discover how the aeroplane concerned can maximize its excess thrust, and therefore maximize its climb angle, it will be necessary to see the thrust and drag data. Let us first deal with the data for a jet aeroplane. Shown here is a typical graph of total thrust available and total drag for a jet-powered aeroplane. Excess thrust available is the amount of thrust that exceeds drag. Here, excess thrust available can be seen on the graph as the area between the thrust and drag lines. You will recall that to maximize the gradient of climb, excess thrust available must be at a maximum. This is the case where the distance between the thrust and the drag lines is the greatest, as shown here. Notice that maximum excess thrust available occurs at this speed. At any other speed, the excess thrust available is less, and therefore the climb angle achievable will be less than maximum. The speed at which the aeroplane generates the greatest amount of excess thrust, and therefore is capable of its greatest angle of climb, is called Vx. Vx is defined as the speed for the best angle of climb. However, in order to appreciate what value this speed represents, it is necessary at this point to mention some other speeds. There are 3 such reference speeds which are used in aeroplane performance. The first is a speed called the velocity for minimum drag, or VMD. VMD speed is found at the bottom of the drag curve, as shown. The second reference speed is called the velocity for minimum power required, or VMP. VMP is about 0.76 of VMD, as shown here. The last reference speed is found at the tangent point to the drag curve, as shown. This reference speed is 1.32 times the velocity of minimum drag, and its value is referred to as 1.32 VMD. Having identified the reference speeds, it is now more useful to remember that for a jet aeroplane, the speed for the best angle of climb, Vx, occurs at VMD. Flying at VMP, or 1.32 VMD, would not generate the same value of excess thrust, and therefore not generate as steep an angle of climb as would be achievable if the aeroplane were flying at VMD. Having discussed the concept of maximum excess thrust and the speed Vx for a jet, let us now examine these concepts as they apply to a propeller aeroplane. Shown here is a typical graph of total thrust available and total drag for a propeller-powered aeroplane based on sea level performance. Now, excess thrust is the amount of thrust able to be developed by the engine in excess of drag, and it can be seen on the graph as the area between the thrust and drag lines. You will recall that to maximize the angle of climb, excess thrust available must be at a maximum. This is the case where the distance between the thrust and the drag curves is the greatest, as shown here. Notice that maximum excess thrust occurs at this speed. At any other speed, the excess thrust available is less, and therefore the maximum achievable climb angle is shallower. Therefore, Vx for a propeller aeroplane occurs not at VMD like the jet aeroplane, but rather at VMP at sea level, and will increase with altitude. Let us now examine what factors alter the excess thrust available, and therefore the angle of climb. The first of the factors to consider is the effect of weight. Shown here is an aircraft in a steady climb. If we increase the weight of the aircraft, notice that the aeroplane will have more weight apparent drag. The forward and rearward forces are not balanced, and the aircraft will decelerate. In order to maintain speed in the climb angle will need to be reduced, so that weight apparent drag is less. Now you can see the forces are once again balanced, but the climb angle is shallower. This effect can also be observed in the formula for the gradient of climb. If the weight increases, then the division is by a higher number, and so the gradient of climb will be less steep. Weight has another effect on the angle of climb though. An increase in weight will require an increase in lift. If lift is increased, then lift-induced drag will increase. which in turn will increase total drag. This increase in drag will reduce the excess thrust available. Notice now that the present value of excess thrust is not able to balance all of the weight apparent drag. Therefore, the aeroplane climb angle must be decreased to reduce the weight apparent drag to a value that can be balanced by the present value of excess thrust. However, the effect of weight on drag is a bit more complicated. Shown here is a graph representing induced drag, parasite drag, and the total drag. You may recall that it was stated that increasing weight will require more lift. Creating more lift will increase induced drag, and as a result, the induced drag curve will move upwards. Notice, though, that the total drag curve has moved as well. In fact, it has moved slightly upwards and towards the right. The fact that increasing weight moves the total drag curve up and right is an important one to remember and understand. Returning to the excess thrust graphs for the propeller and jet aeroplane, it is now possible to see the effect of the movement of the total drag curve. Increasing weight moves both total drag curves up and to the right. Notice, as mentioned earlier, that there is a decrease in the excess thrust available, and therefore a decrease in the maximum achievable climb angle. However, what is important to see is that the speed for maximum excess thrust available is higher. Therefore, for both jet and propeller aeroplanes, as weight increases, the speed Vx will increase. This means that although your climb angle will decrease with a higher weight, in order to get the best possible climb angle from this deteriorated performance situation, you will have to fly at a higher speed. In Part 1 of the General Performance Principles climb lesson, you learned about the angle of climb, the best angle of climb speed, and lastly, about some of the factors that affect the climb, namely aircraft mass. In Part 2, you will continue the study of what factors affect the climb angle, starting with the effect of aircraft configuration. The next factor that affects the climb angle is the configuration of the aircraft. By configuration, we mean whether the flaps and undercarriage are deployed or not. If the undercarriage and flaps are deployed, then parasite drag will increase. More drag means that there is less excess thrust available. Notice now that the excess thrust is not able to balance all of the weight apparent drag. Therefore, the aeroplane's climb angle must be decreased to reduce the weight apparent drag to a value that can be balanced by the excess thrust. However, the effect of the gear and flaps on drag is a bit more complicated. Shown here is a graph representing induced drag, parasite drag, and the total drag. You may recall that deploying the undercarriage mainly increases parasite drag, and as a result, the parasite drag curve will move upwards. Notice, though, that the total drag curve has moved as well. In fact, it has moved slightly upwards and towards the left. The fact that deploying gear and flaps moves the total drag curve up and left is an important fact to remember and understand. Returning to the excess thrust graphs for the propeller and jet aeroplane, it is now possible to see the effect of the movement of the total drag curve. Lowering the flaps and undercarriage moves the total drag curves up and left. Notice, as mentioned earlier, that there is a decrease in the excess thrust available, and therefore a decrease in the maximum achievable climb angle. However, what is important to see is that the speed at which maximum excess thrust is available is lower. Therefore, for both jet and propeller aeroplanes, as the gear and flaps are deployed, the speed for maximum angle of climb, Vx, will decrease. This means that although your climb angle will decrease with gear and flaps deployed, in order to get the best climb angle from this deteriorated performance situation, you will have to fly at a lower speed. It therefore seems prudent not to use flaps during the climb so that the climb angle is as large as possible. But you may recall that flaps helped improve the overall takeoff performance. So if you do use flaps for takeoff, when it is safe to do so, remove the flaps in stages. Consult your aircraft manual for precise instructions. The next factor that affects the climb angle is the density of the air. Density has a direct influence on the thrust produced by an engine. Decreasing density will reduce the mass of the air available for a jet engine and reduce the oxygen content available for combustion in a piston engine. Therefore, as density decreases, the thrust of both jet and propeller aeroplanes will decrease. Returning to the excess thrust graphs for the propeller and jet aeroplane, it is now possible to see the effect of decreasing density. Decreasing density will reduce the thrust and therefore cause both thrust curves to move downwards. Notice that the excess thrust continually decreases, and therefore the angle of climb continually decreases. An important point to note is that Vx remains constant with changes in density. However, you will recall that when density decreased, true speeds increased. So, although the speed Vx is constant with decreasing density, the true airspeed for Vx will of course increase. The most notable and testable part of the effect of density on the angle of climb will be through altitude. As the altitude increases, density will decrease and the angle of climb will steadily decrease. You will recall from an earlier lesson that high temperatures and high humidity also decrease air density and decrease aeroplane performance. The next factor that affects the climb angle is the wind. However, the effect of wind varies according to what type of gradient is being discussed. There are two types of climb gradient we need to look at. The first is the air gradient. This gradient is calculated using the horizontal air distance against the vertical distance. The start point of the gradient is air-based. If there is a headwind, notice that the start and end point of the climb, being measured relative to the moving air, are being pushed backwards. However, the climb angle relative to the air is still the same. If there is a tailwind, the same considerations apply. The start and end point of the climb, being measured relative to the moving air, are being pushed forwards this time. But, as before, the climb angle relative to the air is still the same. An important point to retain about the air gradient is that winds have no effect on them. Air gradients are used by aviation authorities to lay down minimum climb performance limits. For example, a multi-engine aeroplane operating in the public transport category must demonstrate a 4% air gradient after takeoff. This requirement forms part of the operational safety standards that were mentioned in the performance standards lesson. The second type of gradient is called the ground gradient. This gradient is calculated using the horizontal ground distance against the vertical distance. Unlike the air gradient, this time the start point of the gradient is fixed in relation to the ground. If there is a headwind, notice that the aircraft, relative to the previous path, is being pushed backwards and will cover a reduced horizontal ground distance. The result is that the climb angle increases. Therefore, headwinds will increase the ground gradient. Likewise, with a tailwind, the aircraft is being pushed forwards and will cover a far greater horizontal ground distance. The result is that the climb angle decreases. Tailwinds, then, will decrease the ground gradient. The reason why it is important to understand how headwinds and tailwinds affect the ground gradient is because ground gradients are used to calculate obstacle clearances. If there was an obstacle, like the one shown on screen, then if a tailwind were present, the aeroplane would not clear it. When making calculations to assess obstacle clearance performance, the climb gradient must be adjusted to take into account the effect of the wind. If we wish to manually correct the gradient for the effect of wind, the air gradient must be multiplied by a wind factor to obtain the ground gradient. When applying the wind factor, the formula we use is the climb gradient multiplied by the true airspeed over the true ground speed. Let us assume an air gradient of 12% with a true airspeed of 100 knots and a headwind of 20 knots. This makes the true ground speed 80 knots, giving a wind factor of 1.25. Therefore, the factor to use in this case is 1.25. Multiplying the air gradient of 12% by the factor 1.25 will give a ground gradient of 15%. If the example were a tailwind, the air gradient would be multiplied by the wind factor, which would decrease the ground gradient. There is one additional complication. If the ground gradient is to be used for the calculation of obstacle clearances, the application of headwinds and tailwinds in the wind factor calculation must include the 50% headwind and 150% tailwind rules that you learnt about in the previous lesson. Returning to the example then, if the wind rules are applied, only 50% of the headwind should be used, meaning that only 10 knots rather than 20 knots should be used in the calculation of the ground speed. This makes the true ground speed 90 knots instead of 80 knots, and the resulting wind factor is 1.11. This makes the ground gradient 13.3%. It is important to understand when to use the 50% and 150% wind rule. In the case of climbing, use this rule whenever you have to calculate your obstacle clearance capability. In the previous scene, you learned how to calculate the correct ground gradients for use in obstacle clearance problems. This part of the lesson will deal with those obstacle clearance problems. Firstly, let us examine a simple formula which puts into perspective this particular type of problem. The gradient is actually a ratio of the vertical and horizontal components of the climb, expressed as a percentage. Shown on screen is the formula to calculate the gradient. Rearranging the formula also allows us to calculate the horizontal and/or the vertical components. Now let us work through an example. Following a takeoff, a light twin-engine aeroplane climbs on a 10% climb gradient. By how much will it clear a 900-metre high obstacle situated at 10,000 metres from the 50 feet clearance point? In order to find out by how much the aeroplane will clear the obstacle, it is necessary to calculate the height the aeroplane will attain after covering a horizontal distance of 10,000 metres. Using the formula at the top left-hand side of the screen, you can see that to calculate the vertical, the gradient must be multiplied by the horizontal. This makes the equation 10% multiplied by 10,000 meters, divided by 100. The answer is 1,000 meters. This means the aeroplane will gain a height of 1,000 meters after covering a horizontal distance of 10,000 meters with a 10% climb gradient. However, the question stated that the aeroplane was at the end of the takeoff distance, and therefore at the screen height. In order to calculate the aeroplane's height above ground level, we must add the screen height, which is approximately 15 meters. We can now calculate the clearance. The aeroplane has attained a height of 1,015 meters above ground level, and the obstacle is 900 meters above ground level. Therefore, the clearance is 115 meters. You may recall that there were two primary ways of analysing the performance of the aircraft in a climb, namely the angle of climb and the rate of climb. Having completed the gradient and angle of climb section, let us now focus on the rate of climb. The rate of climb is the vertical speed of an aeroplane measured in feet per minute and shown in the cockpit by the vertical speed indicator, or VSI. Another way to consider rate of climb is to see it as the velocity of the aeroplane along a gradient. Let us assume that two identical aircraft have the same angle of climb, but the one on the right has a faster speed along the gradient. Notice that over a given time, the aeroplane on the right climbs through a higher vertical distance than the aeroplane on the left. Therefore, the aeroplane on the right has a higher rate of climb. This demonstrates that forward speed is an important factor in the rate of climb. Equally though, if two identical aeroplanes have the same forward speed, but the aeroplane on the right travels along a steeper angle, in a given time, the aeroplane on the right climbs through a higher vertical distance than the aeroplane on the left. Therefore, the aeroplane on the right has a higher rate of climb. This demonstrates that angle of climb is also an important factor in the rate of climb. From this simple demonstration, it can be seen that the rate of climb is a function of both angle of climb and speed along the achieved gradient. Let us return to the formula for the gradient of climb, as shown here. Gradient is given by the formula thrust available minus thrust required divided by weight. All that is needed now is to add the velocity function as shown. This is now the formula for the rate of climb. However, there is a little more detail to understand. The velocity in this case is true airspeed. Thrust and drag are both forces. Velocity is distance over time. Force multiplied by distance gives work. Work divided by time gives power. This means that instead of thrust multiplied by velocity, the formula now contains the expression power available, and instead of thrust required multiplied by velocity, the formula now has power required. The formula now reads power available minus power required, which gives excess power divided by weight. For any given weight, the greater the excess power available, the larger the rate of climb. Conversely, the lower the excess power available, the smaller the rate of climb. In order to maximize the aeroplane's rate of climb, therefore, we need to maximize the excess power available. Shown here is a graph of power available and power required for a typical jet aeroplane based on sea level performance. In order to provide a benchmark for the next part of the lesson, it is necessary to locate the 3 reference speeds we mentioned earlier in the lesson. The speed found at the bottom of the power required curve, shown here, is called the velocity for minimum power, or VMP. There was another speed, slightly faster than VMP, called VMD. This speed is the velocity for minimum drag and is found at the tangent to the power required curve. Lastly, the highest of the performance reference speeds is 1.32 VMD, which is located a point beyond VMD. Having analysed the reference speeds, the object now is to locate where excess power available is maximum. The area between the 2 curves represents the area of excess power. On the graph, the greatest amount of excess power available will be found where the distance between the curves is at maximum, as shown here. Notice that it occurs at this speed. At any other speed, the excess power is less, and the rate of climb will be less. The speed for the best rate of climb is called Vy. For a jet aeroplane, you will notice that under sea level conditions, this speed occurs at 1.32 VMD and will decrease as height increases. Vy is the airspeed to use to climb to the cruise or en route altitude, as it will give the greatest height gain per unit time. In a typical 737-400, this speed is about 275 knots and is usually published in the aeroplane flight manual as an indicated airspeed. Shown here is a graph of power available and power required based on sea level for a typical light aircraft. On the graph, the greatest amount of excess power available will be found where the distance between the curves is at a maximum, as shown here. At any other speed, the excess power is less and the rate of climb less. As we have already learnt, Vy is the speed for the best rate of climb. For a propeller aeroplane, you will notice that this speed occurs at VMD under sea level conditions and will decrease with height gain. It is important to remember where Vy is found for both jet and propeller aeroplanes. For example, looking at the graph, it can be seen that if a propeller aeroplane were climbing at a speed equal to VMP and then selected a slightly higher speed, the excess power would increase and the rate of climb would increase. It is easy to see how speed changes affect both excess power and the rate of climb when the graph is used. Try and become aware of what the graphs look like so that you can use them to your advantage in test situations. Let us now examine what factors can influence the rate of climb. The first of these factors is aeroplane weight. You may recall that an increase in weight creates more weight apparent drag, which reduces the angle of climb. For any given airspeed, if the angle of climb reduces, then so will the rate of climb, because they are fundamentally linked. Weight has a further effect, though, that we have already talked about. An increase in weight will require an increase in lift. Increasing lift increases induced drag, which causes the drag curve to move up and right. The power required curve, shown in red, is actually based upon drag. Power required is drag multiplied by velocity. So, if the drag curve moves up and right, so will the power required curve. This results in less excess power available, and therefore a decrease in the rate of climb. The power graphs for both jet and propeller demonstrate this. However, what is important to see is that the speed for maximum excess power available is no longer the same. It is now higher. So with higher weight, the rate of climb is decreased, but Vy is increased. The next factor that affects the rate of climb is the configuration of the aircraft. In other words, the use of flaps and undercarriage. If the undercarriage and flaps are deployed, then the profile drag of the aeroplane will increase. This increases total drag, and the drag curve moves upwards and to the left. The power required curves will follow the same movement as the drag curve. Notice the reduction in excess power available, as shown by the blue double-headed arrows. You may recall that a reduction in excess power reduces your rate of climb. However, the important effect here is that the speed for maximum excess power is no longer the same. It is now lower. So, with the undercarriage and/or flaps deployed, the rate of climb is decreased and Vy is decreased. If you use flaps for takeoff, remove them in stages when you have attained a positive stable climb, ensuring you check through the aeroplane flight manual for the correct actions for your aeroplane. As you retract the flaps, the rate of climb and the speed to attain the best rate of climb will increase, so you should accelerate to ensure you remain at Vy. In Part 3 of the General Performance Climb lesson, you learnt about the rate of climb, the best rate of climb speed, and lastly, about some of the factors that affect the rate of climb, namely aircraft mass and configuration. In Part 4, you will continue the study of what factors affect the rate of climb, starting with the effect of air density. Density is another important factor that affects the rate of climb. However, density also affects a lot of the variables in the formula for the rate of climb. Shown here is an expanded rate of climb formula, reminding you that power available is thrust multiplied by true airspeed, and that power required is drag multiplied by true airspeed. Let us just focus on the power available for the moment. Decreased density will decrease the thrust, but it will also increase the true airspeed. The overall effect is that the thrust loss is more than the TAS gain, meaning overall that the power available decreases. Looking at power required, decreased density will increase the true airspeed, but have no effect on the drag. Therefore, the power required will increase. Returning to the graph, this means that the power available curves move down and right, and the power required curves move up and right. You will notice that there is less excess power available, and this causes a reduction in the rate of climb for both aeroplane types. This effect will be repeated any time the density falls, which can either be by increasing altitude, increasing temperature, or by increasing humidity. We stated just previously that the true airspeed for Vy increases with decreasing density. As pilots, we fly using indicated airspeeds, and therefore it is important to understand what happens to the indicated airspeed of Vy. In order that we may understand, a further explanation is needed. Shown on screen is a graphical representation of the relationship between indicated airspeed and true airspeed with altitude. We have already stated several times that with decreasing density or increasing altitude, in order to maintain the same indicated airspeed, the true airspeed must increase. The graph here shows the true airspeed increasing for a constant indicated airspeed. However, returning back to Vy, it was stated that the true airspeed for Vy increases slightly with altitude as density decreases. You'll notice that if the true airspeed increases slightly with altitude, the indicated airspeed will fall. In fact, Vy will eventually fall to become the same value as Vx. This means that Vy, expressed as indicated airspeed, is actually decreasing as altitude increases. So, in summary, reduced density decreases the indicated airspeed of Vy and decreases the rate of climb. The higher the aeroplane flies, the more the excess power available diminishes, and therefore the maximum achievable rate of climb will decrease. There will be an altitude where the excess power available decreases to zero, as shown. Therefore, the rate of climb will also decrease to zero. This altitude is known as the absolute ceiling. The graph on screen shows the excess of power for a typical aeroplane at MSL. Notice Vy is the speed that gives the maximum excess power available and maximum achievable rate of climb. As altitude increases, notice that the excess power available, achievable rate of climb, decreases and the indicated airspeed for Vy decreases. At its absolute ceiling, the performance of an aeroplane is so reduced that it is unable to maneuver. Therefore, absolute ceiling is a rather abstract concept for a pilot. It is more useful for a pilot to know his aeroplane's service ceiling. Service ceiling is defined by the manufacturers and aviation authorities as the maximum altitude where the best rate of climb airspeed will still produce a positive rate of climb at a specific number of feet per minute. The recommendation is to not exceed this altitude, because above it the performance envelope of the aeroplane is very small. If the aeroplane were to climb higher, the rate of climb would fall to zero. The aeroplane will not be able to climb any higher, and the absolute ceiling would be reached. At this altitude, Vy and Vx are the same speed. To find the absolute and service ceilings of your aeroplane, consult your flight manual and operate the aeroplane below the service ceiling to help maintain sufficient performance levels. To demonstrate the effect of wind, let us return to the original concept of the rate of climb. You may recall that it was stated that the rate of climb is a function of the gradient and the forward speed. The formula on screen demonstrates this. In the case of a headwind, the gradient increases as shown, but the forward speed is decreased. Looking at the formula, one variable has gone up, the other variable has gone down. The net result on the rate of climb is that it remains unchanged. In the case of a tailwind, the gradient decreases, but the horizontal speed increases. Again, the situation is the same. One variable decreases, but the other variable increases. The net effect is that the rate of climb remains unchanged. Looking at both the headwind and tailwind examples together shows you that both aeroplanes are gaining the same height in the same time. Therefore, we may state that winds do not affect the rate of climb of an aeroplane. The last part of this lesson will deal briefly with some of the formulae you have seen so far, and how to rearrange them to suit various scenarios and questions. This first formula is the formula for the gradient of climb. The triangle on the right is a useful tool to help you rearrange the formula for any required situation. For example, if you are asked to calculate the weight, then the formula would be the thrust minus the drag over the gradient. Or, if you needed to calculate the thrust minus the drag, in other words, the excess thrust, then take the gradient and multiply it by the weight. The second formula relates mainly to obstacle clearance type questions. Earlier on, you were shown a typical obstacle clearance problem, and the formula used was the one shown on screen. Again, using the triangle, it is possible to rearrange the formula. If you were required to calculate the horizontal distance, it would be the vertical distance divided by the gradient. More commonly, you may be asked to calculate the vertical distance. The vertical distance is found by taking the gradient and multiplying it by the horizontal distance. The last formula is very similar to the previous one. Instead of vertical distance, we have vertical speed, which is the rate of climb. Instead of horizontal distance, we have horizontal speed, which is the true airspeed. If you were required to calculate the gradient, then it would be the rate of climb divided by the true airspeed. Or, if you were required to calculate the true airspeed, you would take the rate of climb and divide it by the gradient. Lastly, to calculate the rate of climb, take the gradient and multiply it by the true airspeed. Using these simple triangles to help you rearrange the formula can simplify the mathematical component of the performance exam and allow you to concentrate on the more theoretical performance aspects. This completes the lesson on climb performance. Ensure that you familiarize yourself with how various factors and environmental conditions affect your climb performance in terms of both the angle and rate of climb.